Hi, welcome back to Chapter 3, Section 1, Wave Action. Okay, today we're going to find out how does a wave form and how do waves change near the shore? How do waves affect shorelines and beaches? Hundreds of years ago, kings and queens ruled the islands of Hawaii. If you could travel back in time, you could watch the royal family engaging in the island's favorite sport. It wasn't baseball or tennis or polo. Instead, the ancient rulers paddled into the ocean on heavy wooden boards to catch the perfect wave. They were wave sliding, a sport we know today as surfing. If you've ever seen a surfer like the one in Figure 1, you know they make this difficult sport look almost easy. But even experienced surfers can seldom predict when the next good wave will roll into shore. As you will read in this section, many different forces influence the size, shape, and timing of waves. Okay, what is a wave? When you watch a surfer's wave crash onto the beach, you are seeing the last step in the development of a wave. A wave is the amount of energy through a body of water. Wave development usually begins with the wind. Without the energy of the wind, the surface of the ocean would be as smooth as a mirror. Most waves form when wind blows across the wave surface, transferring their energy into the water. So we just talked about energy and energy transfer in hydroelectric power, that the kinetic energy was transferred into electric energy. So the energy from the wind transfers its energy to the water, causing the waves. Okay? Wave size. Waves start in the open ocean. The size of a wave depends on the strength of the wind and on the length of time it blows. A gentle breeze creates small ripples on the surface of the water. Strong winds create larger waves. The size of the wave also depends on the distance over which the wind blows. Wind blowing across longer distances build up bigger waves. Wind blowing across the Pacific Ocean can create bigger waves than winds blowing across the narrower Atlantic Ocean. Okay? Wave energy. Although waves may appear to carry water toward shore, the water does not actually move forward in deep water. If it did, ocean water would eventually pile on the coast of every continent. The energy of the wave moves towards shore, but the water itself remains in place. Okay, that's important to note. The energy moves, but the water remains in place. Okay? You can test this by floating a cork on a bowl of water. Use a spoon to make a wave. As the wave passes, the cork lurches forward a little, then it bobs up and down. It ends up almost in the same spot. Okay? So, if you had a cork here in a bottle, it's just going to bob up and down because the energy is transferred. So the energy goes like this, but the water is just moving up and down. Okay, so that's what happens in a wave. So all the water doesn't end up on the beaches. Okay, so let's look at this for a minute. Okay, I want you to look at a few things, a few definitions. Okay, so from crest to crest. This is a wavelength. You could also be from trough to trough. This is also a wavelength. Okay? The bottom here is a trough. Okay? The top of the wave here, top of the wave here, those are all called crest. Okay? The distance from the top of the crest to the bottom of the trough is called the wave height. You will need to know these and understand these for the test, but also when we're talking about this week. Okay? So the particle motion. So when we have a particle motion, you see the particles moving like this. Okay? The particles move. Okay? So the energy is transferred. So the wave moves in a direction. but the water doesn't move, just the energy moves, okay? So, as a wave passes, water molecules move in a circular motion. The buoy on the surface swings down into the trough of one wave, then back up to the crest of the next. Below the surface, water particles move in small circles at a depth equal to about 1/2 the wavelength. Water particles are not affected by the surface wave. Okay? Water motion. Figure 2 shows what happens to the water as a wave travels through. As the wave passes, water molecules move in a circular path. They swing forward and down with the energy of the wave, then back up to the original position. Notice the deeper water particles move in smaller circles than those near the surface. The wind affects the water at the surface more than it affects the deep water. Below a certain depth, the water does not move at all as the wave passes. If you were inside a submarine in deep water, you would not be able to tell whether the water was above you was rough or calm. Okay, other wave characteristics. Scientists have a vocabulary of terms to describe the characteristics of a wave. The name for the highest part of the wave is a crest. The horizontal distance between two crests is called the wavelength. We already pointed that out. Long rolling waves with lots of space between the crest have long wavelengths. So those are long wavelengths, where you could have short wavelengths. Short, choppy waves have shorter wavelengths. Waves are also measured by their frequency, the number of times that passes a point at a certain amount of time. So the frequency would be how many times the crest passes a certain point within a specific amount of time. The lowest part of a wave is the trough, okay? The vertical distance from the crest to the trough is the wave height. Remember, that was the part that went up and down like that. The energy and strength of a wave depends mainly on its wave height. Okay, so if you have a shallow wave that has a smaller wave height, it's not going to be a very big wave. But then when you have a tsunami, you would have a huge wave height, which would mean you'd have a huge amount of energy coming towards you. Okay, in the open ocean, most waves are between 2 and 5 meters high. During storms, waves can grow much higher and more powerful. Okay? How waves change near shore. Okay, again, remember we talked about wavelengths being important and wave heights being important. So keep that in the back of your mind as we're talking through this. Okay? Have you ever seen an area of ocean water swelling, resulting in a wave? Waves begin this way out in the ocean, but as they approach the shore, they change. Breakers. The white-capped waves that crash on the shore are often called breakers. In the deep water, these waves usually travel as long, low waves called swells. As the waves approach the shore, the water becomes shallower. Follow the waves in the figure 3 as they enter the shallow water. The bottom of the waves begin to touch the sloping ocean floor. Friction between the ocean floor and the water causes the waves to slow down. As the speed of the wave decreases, their shape changes. So as the waves get to the ocean, to the shore, their shape changes. So near the shore, wave height increases and wave length decreases. So they're going to go from long, short waves to really short but high waves. That's what happens when it hits the ocean floor, okay? As the wave breaks, it continues to move forward. At first, the break surges on the beach, but soon gravity slows it down, eventually stopping it. The water that had rushed up the beach then flows back and out to the sea. Have you ever stood at the water's edge and felt the pull of the water rushing back out to the ocean? This pull, often called an undertow, carries shells, seaweed, sand away from the beach. A strong undertow can be dangerous for swimmers. So let's look and see what happens. Notice that we have long wavelengths here. Okay. And they're not very high. The height is small. But as you get to the ocean, look what happens. The waves get shorter, but the height increases, and then it forms a breaker when it hits the beach, okay? Friction with the ocean floor, so this is the ocean floor here, causes waves to slow down in the shallow water near the shore. The wave height increases until the wave breaks, forming the surf, okay? So tsunamis. So far, you've been reading about waves that are caused by the wind. Another kind of wave, shown in figure 4, forms far below the ocean surface. This type of wave, called a tsunami, is usually caused by an earthquake. So you can see the earthquake right here. Beneath the ocean floor. The abrupt movement in the ocean floor sends pulses of energy through the water above it. When tsunamis reach the coast, they can be as devastating as an earthquake on land, smashing buildings and bridges. Okay, at sea, a tsunami travels as long, low waves. So notice we had long, low waves here. The wave height increases suddenly. So you see, this is a house. See how big this wave height is. That's why tsunamis are so dangerous. The whale of the water smashes onto land, tossing ships onto shore and destroying tall buildings. So notice how the wave height and the wavelength decreases, wave height goes huge, right before it hits the shore. Despite the tremendous amount of energy a tsunami carries, people on a ship at sea, the people on a ship at sea may not even realize the tsunami is passing. How is this possible? A tsunami in deep water may have a wavelength of 200 kilometers or more, but a wave height of less than a meter. When the tsunami reaches shallow water near the coast, friction with the ocean floor causes the long waves to decrease suddenly. The wave height increases and the water piles up. The tsunami becomes a towering wall of water. Some tsunamis have reached heights of 20 meters or more, taller than a 5-story building. Tsunamis are more common in the Pacific Ocean, often striking Alaska, Hawaii, and Japan. In response, nations in the Pacific had developed a warning system which can alert them to an approaching tsunami. But not all tsunamis occur in the Pacific Ocean. On December 26, 2004, a major earthquake in the Indian Ocean caused tremendous tsunamis that hit 11 nations. Tragically, these tsunamis took the lives of more than 230,000 people. Several nations are now developing a tsunami warning system for the Indian Oceans. Okay. How waves affect the shore. What happens on shore as waves pound the beach? Figure 5 shows some of their effects. Because wave direction at sea is determined by the wind, waves usually roll towards the shore at an angle, but as they touch bottom, the shallower wave slows the shoreward side of the wave first. These rows of waves gradually turn and become more narrowly parallel to the shore. Okay, longshore drift. As waves come into the shore, water washes up on the beach at an angle, carrying sand grains. The water and sand runs back down to the beach. This movement of sand along the beach is called a longshore. So it's a movement of the sand. As the waves slow down, they deposit the sand they are carrying on the shallow underwater slope in a long ridge called a sandbar. Okay. Here's longshore drift here. Waves approach the shore at an angle. This results in a gradual movement of sand along the beach. Okay, so here is our movement of sand. This is the direction of the incoming wave, and it's at an angle. And then the direction of the longshore drift goes this way. Okay, so it moves the sand. Rip currents. As the sandbar grows, it can trap the water flowing along the shore. In some places, water breaks through the sandbar and begins to flow back down the sloping ocean bottom. This process creates a rip current, a rush of water that flows rapidly back to the sea through a narrow opening. Rip currents can carry swimmers out into the deep water. Because rip currents are narrow, a strong swimmer can usually escape by swimming across the current parallel to the beach. Okay? In what direction does a rip current pull a swimmer? It pulls them down towards out into the open ocean, but a swimmer should swim parallel to the beach to try to escape the rip current. So here's the rip current, and here's the sandbar that the longshore drift has created. Okay. Okay, a barrier beach. Barrier beaches are sand deposits that form parallel to a shore. Sand dunes are hills of wind-blown sand that helps protect the beach. Okay, waves and beach erosion. The boundary between land and ocean is always changing shape. If you walk on the same beach every day, you might not notice that it is changing from day to day. Waves remove sand and bring new sand at about the same rate. But if you visit a beach just once a year, you might be startled by what you see. Waves shape a beach by eroding the shore in some places and building it up in others. At first, waves strike a rocky shoreline, carve the rocks into tall cliffs and arches. Over many thousands of years, waves break the rocks into pebbles and grains of sand. A wide sandy beach forms. Then the waves begin to eat away at the exposed beach. The shoreline slowly moves farther inland. Longshore drift carries the sand along the coast and deposits it elsewhere. This process of breaking up rock and carrying it away is known as erosion. Barrier beaches. A natural landform that protects shorelines from wave action occur along low-lying beaches. Long sand deposits called barrier beaches form parallel to the shore. Such beaches are separated from the mainland by a shallow lagoon. Waves break against the barrier beach instead of along the land inside. For this reason, people are working to preserve natural barrier beaches like those of Cape Cod, the New Jersey shore, and the Georgia and Carolina coasts. Okay, sand dunes. Other natural landforms also help protect beaches and reduce erosion, although they cannot completely stop the movement of sand. Sand dunes, which are hills of windblown sand, can make a beach more stable and protect the shore from erosion. The strong roots of dune plants, such as beach grass and sea oats, hold the sand in place. These plants help to slow erosion caused by wind and water. But the dunes and plants can be destroyed by cars, bicycles, and even many people walking over them. Without plants to hold sand in place, dunes can easily be washed away by wave action. Groins. Many people live near the ocean, but over time erosion can wear away the beach. This threatens the homes and other buildings near the beach. To avoid losing their property, people look for ways to reduce the effect of erosion. One method of reducing erosion along a stretch of beach is to build a wall of rock or concrete called a groin. Outward from the beach, sand carried by the water piles up against the groins instead of moving along the shore. Figure 7 shows how groins interrupt the movement of water. However, groins increase the amount of erosion farther down the beach. So you can see here that they have made a barrier here. So they have protected their homes with this groin. But then erosion happens more further down the beach. So you can see that for some parts it's good, and for other people it would not be so good, okay? All right, we are done with this section. Please do section 1 assessment, and I will see you again next time. Bye.